This is your lesson on evaluating and simplifying polynomial expressions and equations. It's going to follow the notes in Glen Co 5.2, 5.3, and 7.1. We're first going to start off looking at example 1, where we're determining whether an expression is a polynomial, and if it is, we're going to state the degree. In A, notice that we have two terms. That means we're called a binomial here. And we're also making the observation that our exponents of our variables are integers as well as positive numbers. To determine the degree, I'm now going to look at their exponents and determine what the highest power is, which is the sum of their two exponents. Looking at our first term here, we're going to have a 3 and a 5, which makes this polynomial a degree 8. Okay? Now, what's holding b back? The reason he is not a polynomial is this term, the square root of x. If you remember from our rational exponents, that means he's really just x to the 1/2 power. And because he has a fractional exponent, it makes it not a polynomial. Okay? Next, we're going to take a look at example 2, where we're subtracting and simplifying a polynomial expression here. Subtraction is most certainly the most concerned operation because we need to recognize we are subtracting each term inside the set of parentheses here. So we're going to have 3x squared, and we're going to subtract the x squared. The reason I just pair them together is because they're like terms. I'm also going to pair together the negative 2x, and I'm going to subtract from him the 4x. The other terms are my constants. We're going to have a 3, and we're going to subtract a negative 2. Okay? Well, 3x squared minus x squared, that's going to get us 2x squared. Negative 2x minus 4x is going to get us negative 6x. And our last one, 3 minus negative 2 becomes a plus, so we're going to have 3 plus 2 plus 5. Okay? All right, our multiplication example is just multiplying a monomial into a trinomial. So I'm going to take this 2x and multiply it into each of the three terms within my set of parentheses. So I'm going to have 2x times 7x squared. I'm going to have a 2x times a negative 3x. And I'm also going to have a 2x multiplied by a 5, okay? And we're going to be adding these terms together because they're each individual terms. It's going to produce the three terms. So first guy, 2x times 7x squared gets me 14x to the third, okay? 2 times 7 is 14. And an x times an x squared gets me x cubed. Now over here I have 2 times negative 3 giving me a coefficient of negative 6. And x times x is going to get me x squared. Okay? And then the last guy we have is 2x times 5, which gets us 10x. We're now looking at example 4, where we're multiplying two binomials. Another common way to express how to multiply two binomials is just our FOIL. You'll probably hear me say that a lot anytime I see two binomials. And what I mean by foiling is I'm going to take the first term and multiply it by the first term in my second set. So 3y times 5y is going to get me 15y squared. I'm now going to take the first term here and the outside term on the last guy, that's the O, and multiply them. 3y times 4 gets me 12y. Now I'm doing the I, which is the inside numbers, the 2 times the 5y, getting me 10y. And then lastly, I'm going to do the last terms, 2 times 4, getting me 8. The last thing I need to check for to see is if I have any like terms. So notice that 12y and 10y can be combined, leaving me with my final answer of 15y squared plus 22y plus 8. Okay? Now we're multiplying polynomials in example 5, and you can follow the same general idea of foiling, but it's not called foiling anymore because we're actually going to be multiplying a trinomial by a binomial, and there's a lot more to multiply. So let's get started. N squared times the n is going to get me n to the third. N squared times the 4 is going to get me 4n squared. Now I'm going to move into my 6n, and I'm going to distribute him into both of the terms in my binomial. So 6n times n is going to get me 6n squared, and 6n times 4 is going to get me 24n. I know you're probably noticing that we have terms to combine, but we'll deal with that last. Now I have negative 2. I'm going to distribute him to the n and the 4, and I'll get a negative 2n and a minus 8. So now I check for my like terms, and I'm going to notice first off that I have two terms that have an n squared, And then I also have two terms that just have a singular n. So this is going to simplify my polynomial, leaving me with n cubed plus, well, 4n squared plus 6n squared gets me 10n squared. Next, we have 24n minus 2n. That gets me 22n. And then lastly, we have the negative 8. We're now taking a look at 5.3, looking at the first example where we're dividing a polynomial by a monomial. The recommendation set forth in your book whenever it is dividing by a polynomial is actually one I follow as well. It's really important to recognize that each of the terms in my numerator are being divided by my denominator. It's not a singular action. All three terms in the top are divided by the bottom, which brings me up my next point of it's important to recognize that the only time you're allowed to cancel things out in rational expressions is if they are factors, okay? All right, so now let's take a look here. First guy, first term, I have 4 divided by 4. That's just going to reduce to 1. We're going to have x to the third divided by x, reducing to x squared. And then we're going to have a y squared divided by a y, reducing to a singular y, okay? It's also important that you know your properties of exponents here. Next term, we're going to have 8 divided by 4. That's going to get us a 2. X divided by x produces just 1. And then y squared divided by y is going to reduce to a singular y. Next, we're going to have a negative, because we have this negative outside. 12 divided by 4 reduces to 3. X squared divided by x reduces to x. And then y to the third divided by y reduces to y squared. All right, we're now going to do a little bit of a throwback here to some long division back from elementary school. So we're using long division now to divide polynomials. So we have our little divisor here of z minus 4, and he's being divided into z squared plus 2z minus 24. The part underneath my long division symbol, that is called my dividend, okay? So the process that I'm going to follow here is I'm first looking at the z squared. Notice he is the highest degree polynomial of my dividend. And I'm first going to ask myself, z on the outside, z is my divisor. What times z will get me z squared, okay? Well, the answer to that is z. My goal is to be able to distribute him into my divisor in order to cancel out the polynomials beneath him inside the dividend. So z times z got me z squared. Z times negative 4 is going to get me negative 4z. And hopefully you remember you're going to subtract down. Once again, I like to circle the subtraction. That way I just make a little mental note. Z squared minus z, those go away. That was the goal. Next we have 2z minus negative 4z becoming 6z. It's important to recognize negative 24 has nothing to subtract by, which is why he just gets brought down. Now I'm going to continue, and I'm going to ask myself, z times what gets me 6z? Well, the answer is 6. I'm now going to distribute him, once again, into my divisor. 6 times z gets me 6z, and 6 times negative 4 gets me negative 24. Now, once again, we're going to subtract down. 6z minus 6z goes away. Negative 24 minus negative 24 also goes away, giving me a remainder of 0, okay? This is why z minus 4 perfectly divides into this polynomial, leaving me with the quotient of z plus 6. A use of long division is actually to factor polynomials. Maybe you notice the fact that z minus 4 times z plus 6 equals our polynomial, which was our dividend, okay? Now, this is only true if your remainder is equal to 0, okay? So let's look at an example now where our remainder is not going to be 0. When I have this trinomial of t squared plus 3t minus 9, and it's being multiplied by 5 minus t to the negative first power, what that expression is really saying is divide what I circled in red by that polynomial. So what I circled in red, that is my divisor, so I'm going to rewrite him. And notice I rewrite him as negative t plus 5. I'm going to put my divisor in order from highest degree down. And then here is my dividend. And now I'm going to follow the same process of asking myself, negative t multiplied by what goes into t squared? Well, the answer is negative t. I'm now going to take him and distribute him into my divisor. Negative t times negative t gets me t squared. Negative t times 5 gets me negative 5t, and now I'm going to subtract down. T squared minus t squared will cancel out. 3t minus negative 5t becomes a positive 8t. And the negative 9 also gets brought down because he doesn't have anything to combine with. So now I'm going to ask myself, okay, negative t times what will get me a positive 8t? Well, that's going to be a negative 8. I'm now going to take him and distribute him into my divisor. Negative 8 times negative t gets me positive 8t. Negative 8 times positive 5 gets me a negative 40. Now I'm going to subtract down. 8t minus 8t will cancel out, and negative 9 minus negative 40 gets me 31. This is going to end up being my remainder because negative t times anything will never ever produce 31. Okay? So this is our remainder, and the way we're going to write our answer when we divide him out is we're actually going to say the quotient is negative t minus 8 with a remainder of 31. So when we divided this expression, our final answer is we take our quotient and we are going to write an expression where our remainder is going to be placed over our divisor. Okay, so we can just write it 5 minus t here. This is actually going to be my final answer. All right, we're now going to look at example 4 with synthetic division. Synthetic division is actually one of my favorite topics to teach. And the funny story actually goes is that I had my mom teach me Algebra 2, and this is one of the things that she taught me. Best part about it is because one of my ways of remembering it is called Mama. You'll see why in just a second here. So I have this polynomial, 5x cubed minus 13x squared plus 10x minus 8, and I'm being divided by x minus 2. The setup for synthetic division gets a little half box, and it's going to have some space here. What goes inside this half box here is what the 0 is that I'm testing. So if the factor, the possible factor is x minus 2, that means the 0 would be 2 because it's always the opposite sign. So he's going to go in my half box. Now the coefficients of my polynomial here, they are going to go inside up top. So 5, negative 13, positive 10, and negative 8. Now it's important to notice that in the example provided in the textbook, all of my coefficients were present, which means I wasn't missing an x squared term. If I was missing a term, it'd be because his coefficient was 0. All right, so I'm now going to take this 5 and I'm going to pull him down here. Now I'm going to take whatever I pulled down and multiply him by what's in my half box. So 5 times 2. Their product now goes here. That's where the m comes in from Mama. Multiply. The next thing is I'm going to add. So negative 13 plus 10 gets me negative 3. Once again, I'm now going to multiply. So far we have an m and an a. Here comes another m. Negative 3 times 2 gets me negative 6. Now once again I'm going to add. So 10 plus negative 6 gets me 4. Now I'm going to take my 4, distribute him in here, multiply, which gets me 8, and then I'm going to add, getting me 0. Anytime I end up with a 0, what it has shown me is the fact that it is a factor, which means it's also going to be a solution here. So then what is wonderful is the fact that when I took out the x minus 2 from this polynomial, it left me with these numbers. These numbers are going to be the new coefficients for the reduced polynomial, okay? We had something to the third power. When we divided out a factor of x, that's going to reduce it down to a square power, where the 5 is now my leading coefficient. And then I'm going to proceed and decrease by my degree. He was an x squared. The negative 3 is going to be attached to x to the first. And the 4 is just going to be my constant term here. Like I said with long division, what actually this is used for is for factoring here. So far I've started to reduce my factorization, and so this you can always use your Algebra 1 skills and possibly maybe take them down further. Or if I asked you a question to find the solutions, you can always plug that into the quadratic formula. Alright, so now we're going to look at another synthetic division problem in the 5-3. Now we're going to be given a divisor that has a first coefficient that is not 1, okay? So in this scenario here, we're going to rewrite the divisor so that he has a coefficient of 1. And what you need to remember here is what you do to the top, you must also do the bottom, and vice versa here. So if we have a divisor here of 2, we are going to divide everything by 2, giving us our new expression of 4x to the 4th minus, oopsies, there's a 4, minus 2x squared plus 1/2 x plus 2. And we're being divided by the quantity now of x plus 1/2, okay? That's why we're going to be plugging in negative 1/2 into our synthetic division, because if we set this equal to 0, it will give me my solution or possible solution of negative 1/2. So now these are going to be my coefficients that I plug into synthetic division. Notice the term that is missing is x to the 3rd, which is why I must use a 0, because just because he isn't there doesn't mean he should not be used, okay? So now, pull down the 4, we're going to do some multiply add. Half of 4 is 2, but then we have a positive here divided by a negative there, which makes it a negative 2. 0 plus negative 2 is a negative. Half of 2 is 1, and a negative divided by negative, now we have a positive. Negative 2 plus 1 is negative 1/2. Negative 1/2 of negative 1, that's going to be a positive 1/2. 1/2 plus 1/2 gets me 1, and then once again, negative 1/2 of 1 gets me negative 1/2. And then 2 minus 1/2 is going to be 3/2, okay? So now what we must do is we must use this. We have a remainder of 3/2, and if you remember, we're going to take that remainder, and we are going to divide it by what our divisor is. So our divisor was x plus 1/2, okay? The way I always remember it is the fact that denominators on the top always end its way up on the bottom. But what ends up happening is we're going to have 2 multiplied by both of the parts on the bottom here, giving us a remainder of 3 over the quantity of 2x plus, well, 2 times 1/2 is 1, okay? These guys are going to be the new coefficients for our quotient. We were a degree 4, so now we're going to be a degree 3, so we're going to have 4x cubed minus 2x squared minus x plus 1, and then plus our remainder quantity of 3 over 2x plus 1. Hopefully that made sense. The part that you'll probably need to watch out for sure is dividing a fraction by a quantity. Your textbook does a pretty good job of explaining it, so make sure you check that out. All right, on to 7-1. All right, we're now in 7-1, and we're looking at our first example. We're supposed to find the degree, the leading coefficient of each polynomial who is in one variable here. So looking at A, your notes have been fixed since I last printed. This is really being raised to the 4th, and this is really being raised to the 2nd. Because the only variable I see in all 4 of these terms is the variable x, it is indeed a polynomial, but it also follows the polynomial rules because all of our exponents are positive integers. So the biggest degree that I see is a degree 4. That's why this is a 4th degree or a quartic polynomial. And looking at this term here, he also holds our leading coefficient, and his coefficient is a positive 7. All right, the reason B is not a polynomial is because of this term that contains both an x and a y, other than the fact that one of my terms has an x squared, one of them has a y squared, so he is not a polynomial in one variable. Looking at C, we look pretty good, and then all of a sudden we get to this third term here. 1 over x is really the term x to the negative first. And because we are being raised to the negative first power, it makes me not a polynomial. Then looking at D, he is a polynomial because we have an x, an x, and an x, and all of our degrees, or all of our exponents here, are positive integers. So now I'm looking for the one that has the biggest exponent, and that's my last term here. So he should really be rewritten in descending powers, okay? So he can be rewritten like this. So now we answer the question, the degree. Well, he is a 5th degree polynomial, and his leading coefficient is a leading coefficient of -1. The negative is going to be really important for us to look at when we're graphing eventually. Moving into examples 2 and 3, we're going to start evaluating functions. So this is actually a throwback to some Algebra 1. So just like I've done before, I'm going to get you started, and I'm going to have you check your own answers when you give it a shot with the textbook. So I have this polynomial. This is supposed to say f of r. And I'm supposed to evaluate it when r is 1, when r is 2, when r is 3. So all I'm going to do is I'm going to plug in 1 for r, okay? The reason why people tend to get tripped up here when evaluating functions is they forget their order of operations, especially with this first term here. I have 3 times 1 squared. Well, in order of operations, I first need to do my exponents, then I need to multiply. 1 squared is 1, and then 3 times 1 is 3. And then my rest of my expression here, 3 minus 3 is 0, leaving me with 1, okay? Let's do 2 together, then I'm going to have you finish up example 2, parts A and B on your own. So we're going to plug in 2 for r, plug it in everywhere I see an r. So first off, I do my exponents. So 2 squared is 4. 3 times 4 is going to get me 12. Minus 3 times 2 gets me negative 6, and then I have a plus 1. So 12 minus 6 is 6, and 6 plus 1 is 7. Why don't you finish the rest of those? You may need to pause me because actually I'm going to move on, and then check your answers with example 2. When we're looking at example 3, it's not meant to freak you out that I'm having you plug in something a little bit bigger here for x, okay? So I have p of a squared. That means everywhere I see an x, I'm going to plug in a squared, okay? So here, we also need to worry about our properties of exponents. So when I raise a power to a power here, I'm actually going to multiply their exponents. So a to the, 2 times 3 is going to be 6. Then over here, it's important to notice that this 4 on the outside is not being squared. What is being squared is the a squared, and so I'm going to multiply his exponents, getting me a to the 4th. And then lastly, I'm going to have 5 times a squared, no exponents to worry about there, okay? Now, I'm supposed to find the expression q of a plus 1 minus 2q of a. This is a little bit more advanced, but don't worry about it. Q of a plus 1, that just means plug in a plus 1, that quantity in, for x, okay? The second part of this expression is 2 times q of a, so I'm going to put a 2 on the outside, and then in my expression, I'm just going to plug in an a anytime I see an x, okay? So now, let's see if you can finish up this one on your own and check your answers. Notice that this page here, it's just a lot of blanks for you to fill in, so make sure you're looking at your notes. All right, last example for 7-1, and I really like this example because it's going to help you frame up one of your later on learning targets, okay? Let's look at A and B, and we'll have you do C on your own. Looking at A, first thing I want to do is describe what's called the end behavior here. So, the first part of end behavior I have as x goes to infinity. What this quantity really means is to the right. As I go to the right, what does y do? Your textbook, instead of y, just says f of x. So on A, as I'm going to the right, notice that I'm going down, where y is approaching negative infinity here, okay? The other part to my end behavior is saying, well, as x goes to negative infinity. This just means the left, okay? What does y do? Well, as I'm going to the left here, notice that I'm going down, which once again is where y is negative infinity, okay? Because both of the ends are facing the same direction, this tells me that he is an even degree function here, okay? One way you can also notice that in your end behavior is whatever y is approaching. If it's approaching the same thing, we know it's an even degree. To determine the number of real zeros, all I'm looking for is where do I cross the x-axis and how many times do I cross the x-axis. So in this problem, I cross the x-axis twice, so I have 2 real zeros. Depending upon its degree, the other zeros will lie in the complex number plane, okay? All right, let's take a look at B now. Giving myself a little line here. So, end behavior, as x goes to positive infinity, so as we go to the right, notice that our y values are starting to increase. So y is also going to positive infinity here, okay? All right, so then we go the other direction, as x goes to negative infinity, so as we go to the left, notice that our y is getting smaller. Y is going to go down to negative infinity, okay? Because one end is up and one end is down of my curve here, okay, this tells me that it's an odd degree polynomial because they're going in different directions. Notice I also only cross the x-axis in one location, so I only have one real 0, okay? I would like for you to do C on your own and check your answers with your textbook.